Okay, so real quick. Okay, next step. We looked at using order of operations to do two very important things: to simplify expressions, to isolate a variable. Next step is we want to look at solving systems of linear equations algebraically. Okay, so what do we mean when we? I guess real quick, what do we mean when we even talk about a linear system? What does a system mean in that? A system of linear equations. Sometimes we just say linear system. System of linear equations. What would that be? Yeah. What do you think? A system of, what do you think?
Two linear equations with the variables equals.
Okay, two or more. Yeah, it could be more. A system just means more than one of something. So we've got more than one linear equations that are connected. Okay, the variables, say it's x and y, for example, the variables show up in both equations at the same time. Okay, good. So when we have something like that, we want to look at ways that we can solve the system. But actually, I'll go back for just a second. If I start with a linear system, like, let's make one up here. What if we had what does a solution of that linear system look like? Maybe we ought to start off something easier for just a second. What does a solution of just an equation look like? What if I have 2x minus 3 equals 7? What's the equation, or what's the solution of that equation?
X equals something.
X equals something. Well, what would it be?
5.
5, good, right? Okay, and why is that the solution? Go ahead, Jill, say it again.
So if you substitute it for x and you do all the math, it equals 7.
Okay, good. It makes the equation true, but in math, the way we would really say that in math is, this is a solution, and in this case, it's the only solution, but it is a solution to that equation because it satisfies the equation. That's a terminology in math. That's what we would say. It's a solution because it satisfies the equation, meaning it makes it true. Okay? So let's go back to our system. What is a solution to the system of linear equations going to look like? I don't care what it is yet. What's it going to look like? Katie, say it again.
X equals
Okay, that's part of it. X equals something and y equals something. Okay? We have to have both an x and a y value here, don't we? Okay? Because I have two variables there. Okay? Let's just for a second, let's just take the top equation by itself. So x equals 2y plus 4, or x plus 2y equals 4. Let's try that one. Okay? Let's graph this for a second. This is good review for us. How are we going to graph that equation? What do you think? Yes, ma'am.
We gotta put it in point slope.
Okay, we could put it in slope-intercept, I think?
Yeah.
Okay, slope-intercept. What does that amount to? What is slope-intercept form, real quick? Say it again, y equals mx plus b. Good. And what's m? Slope. B is the y-intercept. That's a good strategy. So if we put this into slope-intercept form, then we should be able to identify what the slope and the y-intercept are, and we can sketch a graph of the line. Okay? Now, this is is what's so cool about math is it just all ties together. This is what we were just doing in a sense, right? We're just gonna isolate the y, aren't we? Okay, does that make sense? Algebraically, we wanna get the y by itself and push everything else to the other side, right? Now, really, the way we would describe that in math, believe it or not, is we would be solving for y, but notice that the answer we get is gonna have a variable in it, right? So it's not gonna be a nice, compact, neat answer like what we had yesterday. We're not getting just a number out of this. We would say we're solving for y in terms of x, meaning we're gonna get x's in our answer. We're gonna establish a connection between y and x where y equals some expression involving x. Make sense? We'll get back to this stuff next year in much more detail, but this is good stuff to kind of start thinking about a little bit now. So let's go through that algebra. This is good practice, reinforcement for what we did yesterday. What are the steps we would go through to solve for y or isolate y? Same thing. Subtract 4, good. Subtract x, good. And then divide by 2, right? Because we're just going to reverse order of operations, aren't we? Do all the addition and subtraction first, and then the multiplication and division. So would you agree then, if we do that, we're going to get, let's do it in 2 steps. We get 2y equals what? Okay, good. And here's a way to think about this. I would encourage you to kind of think about this in terms of visual models. If we're trying to keep the y on the left and push everything else the other way, how do we push the x to the right? Subtract it, right? So we're going to push the x over there by subtracting and push the 4 over there by subtracting, right? I'm going to put the x first. How come? It's better in a sense because look where we're trying to go with this. We're trying to go to mx plus b, right? We want the x term first. So thinking ahead, which you want to do in math a lot, we'll put the x term first. Oops. 4 was already there, wasn't it?
Yeah.
Okay, so that's a mess that up. So that's already there. We don't have to do anything with that, do we? It's already on that side. And then you said divide both sides by 2, correct? Okay. So if we divide both sides by 2, voila, we got the y by itself. There it is. What happens over here? Now I've got a common denominator of 2. What can I do with that to make it look like mx plus b? What do you think? Yes, sir. Okay, so we can split it into 2 separate fractions, can't we? It's written as a common denominator, but we could easily just break that 2 apart into each of the 2 separate fractions, agreed? Okay, so then that's going to look like negative x over 2. If we want to write it in this form, though, as something times x, isn't negative x over 2 the same thing as negative 1/2 times x? Okay, we good? So that's how we want to write it. And then 4 over 2, 2. Good. Okay. We're there. So now let's graph this. So how do we go about sketching a graph of a line? And I want to get you prepared for calculus, really. I want to also talk about sketching versus drawing. Now we can be pretty exact with lines. But most of the time in math, when we're just trying to make a quick visual representation of a function, an equation of some kind, then usually we're just going to try to maybe not be perfect, and what we're going to do is called a sketch. Like in Algebra 2, when we sketch, and you probably did this even last year a little bit, when we sketch quadratic graphs of quadratics, we get parabolas, but we're not going to get it perfect because they're hard to draw. But we'll get some key points and kind of get a good sketch going. I'll call this a sketch because we're really only doing 2 points. But lines are easy and exact. How do we sketch or graph lines, though? What's our strategy always? Somebody that hasn't contributed yet. Be brave. What do you think? How are we going to draw a line? Just think practically. Don't think mathematically here. If you're going to draw a line, how are you probably going to do it? If you're using a ruler. Ah, points. What about the points? How many points do we need? Well, we could have 3, but how many do we actually have to have? We only really need 2, don't we, to define a line. So if we can here's always the way that we're going to sketch lines. Easiest way possible would just be create 2 points on the line and then connect and extend, okay? how are we gonna do that? Where's our starting point in this case? I like to talk about it in terms of an anchor point and a second point. What do you think? Where's the first point gonna be? Yes, ma'am.
Y-intercept.
Y-intercept, yeah, okay. So we have a y-intercept of 2, right? So we can just go up 2 places, and there's our anchor point. How are we gonna get a second point? Slope. We'll make a slope triangle, right? We just know the slope tells us if it's -1/2, what's that telling us in terms of instructions? Down 1, rise of -1 over 2. Very good. Okay, so there's our second point. Now all we have to do is just connect and extend, and there's our line. Yes, sir.
Isn't that just -1, not -1/2?
Oh, whoops, you know what I did? Yeah, I went down 2. You're right. I gotta fix that. My graph wasn't very good, was it? I thought I was going down a line. So that last point, gotta go down 1 and over 2, so it's gonna be right there, isn't it? That better? Agreed? Okay, so now, there's our line, okay? So taking just the example of this top equation, we're not worrying about the other one yet. What's an example of a solution of that equation? While you're thinking, if we go back to this previous example, there was only one solution to this one. That was it. How about here? Is that the case? Somebody give me an example of a solution to that equation. And we got the graph here to help us out. Yes, sir?
X = 0, y = 2.
Exactly. X = 0, y = 2 is a solution, right? So let's keep track of some solutions. One of them is that ordered pair. That's a convenient way for us to write both parts of that, isn't it? We know that x comes first and then comes y. So that's really saying x = 0, y = 2. Good. What's another one? What do you think, Alex?
X = 2, y = 1.
X = 2, y = 1. Very good. Okay. We could keep going. Lily, how many are there going to be if we keep going?
Endless possibilities.
Yeah, there's an infinite number of solutions, aren't there? We could go on and on and on. Here's something really interesting though. What is the connection between each of these solutions and the graph that we created? And this is really cool.
Always equal.
Say it again.
They'll always equal 4.
Equal, what do you mean equal 4?
Like,
The
substitute the points in the equals. They should.
Oh, up here you mean?
Yeah.
Yeah, okay. True. Okay, I'm looking for something else. Now, let's make a connection. Let's just even forget about the equation for just a second. How are these solutions, these ordered pairs, values of x and y that are solutions, how are they connected to the graph? Yes, sir?
There'll always be a point on the graph.
They're points on the line. Ah, okay. Now, how many points make up a line? An infinite number, right? That's one of just the weird things about math. There's an infinite number of points. How many points are there between those 2 points on the line? An infinite number, right? You can kind of think of a line as being like if you had a straight string and you're putting beads on the string. Each bead is a point on the line, but how big would the beads have to be?
Microscopic.
And even less than that, they'd have to be infinitely small, wouldn't they, right? We could fit an infinite number of those beads on there. All right, so really, that line is just what we'd call in math, we call it the locus, meaning it's the collection or the set of all of the points that correspond to the solutions of that equation, gathered up into one entity, one thing, right? Okay. We could do the same thing for the other line too, couldn't we? Right? Here's the other line right here. 3x, remember this, 3x minus 2y = 5. So I'm going to get rid of some of this stuff. I think we're done with this. We got our solution. We graphed our line. That's all we really needed. Now we'll work on the other one. Okay, what was the other one again? 3x = 5. Okay, I'm going to show you another little trick for graphing a line. The first way we did this was we put it into slope-intercept form, great idea, it works. There's another trick here that we'll talk more about, maybe this year, but for sure next year. We can use what's called, it's actually got a name, it's called the Heaviside cover-up method. And it's really a tricky way of graphing a line. All you're gonna do is you're just going to really wisely pick the 2 points that we need to connect and extend. What are the two, kind of thinking out loud here, what are the 2 easiest points to find on a line?
The one axis.
Okay, the points on the axes, right? The intercepts. Now, what's always true at the y-intercept? X is 0, right? Because if it's on the y-axis, that means the x value must be 0, correct? So this is really a good trick. So we could say, okay, let's go ahead. Oh, jeez. Looks like I had some kind of troubles there. We could say, let x equal 0. So we already know that for one of our points, x is going to be 0, right? If I let x equal 0, what happens to this equation?
It always becomes negative 2y equals 5.
Yeah, I get 3 times 0 minus 2y equals 5. That's an easy one to solve, isn't it? Because 3 times 0 is what? Goes away. So you see why we call it the cover-up method? Just cover that up, can't I? If I let x equal 0, I can just cover up that term and solve for y. What's y equal to then? Okay, so if I divide by negative 2, y equals negative 5 halves or negative 2.5, okay? So there's one point, right? We can put that one on there right now. 0, negative 2.5 would be right about there. So there's one point. What's the other one we can find using this trick? The x-intercept. What's true at the x-intercept? Y equals 0. So if y equals 0, wouldn't you agree that term's going to disappear? What's x equal to? 5/3. So we also get the point y equals 0, x equals 5/3. So let's see, that's going to be over 5/3, so that's 1 2/3, so about there-ish. There's my other point, right? If I connect and extend, once again, that line represents the set of all the solutions to that red equation, correct? Infinite number of them. But if I want to find the solution of the system, where do you suppose that sits on this picture? It's where they cross, isn't it? Because the solution to the system has to be the one place where we have an x and y value that satisfies both of those equations at the same time, right? So in terms of a graph, that can only be the one shared point. So you can see it up here right now. It's right there, isn't it? Where does it look like it is? It looks like it looks kind of like x equals 2-ish and y equals 1-ish, right? We don't know if that's right. It's not a very accurate graph, but we could check it and see. So it looks like the solution is at 2, 1. Let's just go back and try it in both and see if it works. Does it? So if I put 2 in here, I get 2 plus, put 1 in there, what do I get? Yeah, 2 plus 2 equals 4. Check. Satisfies the top equation. Is that good enough? No. It's got to satisfy both to be a solution to the system. Let's try this. 3 times 2 is 6 minus 2 times 1. Oops. Was it 1? Oh, so it's not the solution. I thought it was going to be. I screwed up. Oh well. So it's not. It just looks like it is. It's close, but it's going to be a little bit off. Oh well. Next time. But we could find it though. We could find it by using these methods we're going to talk about. It's somewhere close to that, but it's off by a little bit. Okay. But it exists, right? By just looking at these equations, minus all the purple, just the original equations, how could you, without doing the problem, determine how many solutions there were going to be? In this case, there was exactly 1, right? how could we have had a situation where there was maybe no solutions to the system?
If the lines were parallel,
Okay, if the lines were parallel, they would never cross, right? Then they would never share any points, and the system would have no solutions. Can you think of a way where we could have more than one solution?
They're the same lines.
Yeah, if the lines coincided, if they sat right on top of each other, then they'd be the same line and they'd share all their points. Well, how could we tell then, you suppose, what would be the easiest strategy we have for just answering that question? We don't even need to necessarily find the solution, but I want to know, how many solutions does that system have? What do you think? Somebody who hasn't answered yet. What do you think? Maisie, you have any ideas about that? Hi, back there. What do you think? If we wanted to, we said, let's just rehearse what we just said, rehash what we just said. Lines that are parallel would have no solutions. Okay? Lines that were the same line would have infinitely many solutions. But lines that crossed would have one solution. So what would be different about then a line with one solution or the other kinds that were parallel or the same line? What about the slope?
If they cross, they have different slopes.
They have to have different slopes, right? If the two lines have different slopes, you know automatically that system has how many solutions? One, because the lines have to cross one time, don't they? Right? So there's our strategy right there, the start of it. If we just find out what the slopes of these are, maybe by putting them in slope-intercept form, that'd be fine. Then if they're different slopes, done deal, one solution. What if they have the same slope? Then what could be happening there? Could be the same line, or they could be parallel, right? Okay, so then we'd have to see if a point that worked on one of those lines worked on the other one. Does that make sense? You could do that, but we could even maybe make it easier. We could say something like, what if we had these two lines? What if we had the lines, well, it'd be really easy if they were written like this, wouldn't it? If we had y equals 3/2 x minus 11 and y equals 3/2 x plus 2. Are they, slopes are the same. Are they parallel or the same line? Parallel, obviously, they have different y-intercepts, right? If they were written in standard form, so we had something like 2x plus 3y equals 10, and say we had 4x plus 6y equals 8. Okay. Then we probably have to put them in slope-intercept form every time. Okay, I think you got the idea. So let's move on. I'm probably taking more time than I need to with this. Let's take a look then at how we solve these systems. Okay, we want to find, if we can, the one solution or establish that there's no solutions or infinitely many solutions. Okay, we have two methods for this. Do you remember these? Substitution and, did you call it elimination or linear combination? Linear combination, okay. So, oops, went too fast. So substitution method, that's the one that we're going to use when it's easy to do. Okay, substitution method, we'll go through this. This is the one where we're going to solve for one variable in one of the equations and plug it into the other one. If it's really difficult to solve for a variable in either equation, then don't do it. It's hard. You're going to have lots of fractions to fight, and don't do it. But if it's really simple to isolate a variable, to solve for a variable, then this works great. Okay? Linear combination just works always. It's a good one. I like that one the best. So let's look at an example. Okay, what about this guy? There's our system. Is this a good candidate for the substitution method? It only would be if it were easy to solve for a variable in one of those two equations. Is it? Is one of those variables easy to isolate in either equation? Which one? The y in the top one, right? How come? Okay, good, because it has a coefficient of 1 or negative 1. What's the coefficient? the number in front of the variable. Yeah, so this one has a coefficient of -1, right? So it's really easy to get by itself. What are the steps we would have to go through to get to y by itself? Subtract 3x and then divide by -1 or multiply by -1. Yeah, that works. It's not the way I do it. We got a different way. It's fine, but
Subtract 13 and add y.
yeah. What I would do, and this is when you start thinking about this in terms of just moving things horizontally, wouldn't it be easier, we wouldn't have to do any multiplication or division if we just push the y that way and push the 13 that way? Isn't that easy? See what I'm saying? 2 easy steps. We could go, this guy goes over there, this guy goes over there. What's that end up with? So we get on the left side, 3x. On the on the right side? Y. Okay, is it a problem that the y is on the wrong side? No, we can just flip it around, right? Doesn't matter which side goes where. It's an equation. So then we've got the substitution equation, y equals 3x minus 13. I always put a box around that, so you come right back to it. There it is. What are we gonna do with that?
Plug it into the other.
Yeah, we're gonna substitute that into the other equation. So the other equation becomes 2x plus 2 times that, right? 2 times y equals -10. Okay, what goes in there? Now it's easy, right? We're almost there. How many different kinds of variables do we have there? 2. I know, 1. We have 2 different instances of the variable, but there's only one variable in x, right? So all we have to do now is just push all the x's to one side and push the numbers to the other side and isolate the x, right? Collect all the x's. Probably the first step would be maybe distribute. There's a bunch of ways we could do this. 2x, so what's that gonna give us? 2x plus
6x minus 26.
Okay, combining like terms. Okay, while we're at it, let's go ahead and push the 26 this way. 16. Agreed? So x equals? Good. Halfway there, actually much more than halfway there. Now where do we go? Okay, see why I put a box around it? Go right back to the box. There's our substitution equation. We'll plug the 2 right into there, right? Whoops, have a different color. And we just get y equals 3 times 2, we're substituting, minus 13, so what is that? 6 minus 13, -7. So our ordered pair is 2, -7. Okay, don't give up here. On a test, there is no reason to ever miss this. How come? Check it, check it. So plug them back in, does it work?
Yeah.
2, -7. If I put 2 in for x, I get 2 times 3 is 6. Let's see, hang on. Minus -7, what's minus and negative? 6 plus 7, 13, check. We done? Good enough? Oh. It's gotta work in both, right? You gotta check both. How about down here? 2 times 2 is 4, plus 2 times -7, what's that? So 4 minus 14, -10, check. We know we got it. Perfect. Okay, good. All right. And I won't, you guys can, this is on the website already. You can click through this later if you want to, and this goes through everything we just did. Okay? Okay, I'm gonna stop there. We'll hit this tomorrow. Let's go to the lab and, how much time do we have? Oh, we have a little time. We have 15. So let's go, if we can quickly get to a lab, I wanna just make sure I'm taking care of any Moodle issues too.